guess we had a sneak peek of them last time, but again, the idea of a hash table is just like hash browns, like you're trying to chop up data so that you can use it as an index in a lookup table. Okay, it's going to be great. So that's kind of where we left off. So what we got is we really like the idea of this lookup table. Like I'd really like to be able to perform the operations of insertion, like putting something, associating a key with a value, like my name with my phone number, somebody else's name with their phone number. I'd like to make a data structure that supports that operation of inserting a key and a value and looking up with that key, like looking up somebody's name and getting out their phone number. Or looking up their phone number and getting out their name. We know how to do it that way, right? With numbers. But like what if you wanted to use strings? Like how could a string get you somewhere in an array? Because that's what you're doing, right? That's the goal. So like you've got some vector that you'd like to make proportional to the size of things you'd like to insert. Maybe double the size or something. Let's say you want to insert 3 things. So I'll make like a 6 size vector or something. And the goal is you can always, you know how to associate numbers, ints, let's say, with any type. Because, like, think of it like a phone book, reverse phone book, like your phone number to a string their name or string their address. But you could put any type here. This could be like a phone number to a double, like how much money they owe on their phone account. I don't know. Because you can make an array of any kind of t, right? A vector can be made of any type t, and that's the thing that you get when you go to an index. So that's the kind of thing you can put there, anything. But you need to start with an integer, right, to get somewhere, and that is supposed to be a t. For some reason, it does not immediately look like a t to me. So that's kind of what's going on. And so you can map those kind of things, like 3, you can map across to, I don't know, whatever a T is, a name, an address, bank account, just like cloud number 1. You can map 3 there, and you can map 42, maybe. You want the number 42 to be associated with cloud number 2. And you want the number 78 to be associated with cloud number 3. You're putting stuff in places, right? And these are the things you want to use to look up are called the keys. And the things you get when you look up something are the values. Okay, that's the goal. And maybe, I don't know, somehow you know that like these numbers are not quite yet indices. Maybe 3 is fine, it's an index. 0, 1, 2, 3, that one. You can put cloud 1 there maybe. But you have to try to turn these 42s and 78s into indices in the actual table, right? So you got to shrink them down maybe with a modulus. Like maybe that one can go here, number 2 could go there, number 3 could go here. Somehow you've picked a process to do that. And so that's kind of what you get so far. Does that make sense? Is it coming back to us? Like you've got integers, those are your keys. You can map them to anything because you'd make a vector of any of those types, whatever type you want, clouds. And then as long as you have a way of getting these integers like shrunk down to potential indices of this table and they don't clash, you could use those to store stuff and then also go back and look up associated with key number 3. Where was it? Oh, I put it right in this index. Go get the cloud back. Okay, that's kind of how it worked. Are there any questions about that? Does that make enough sense in our brains? It's very simplified, right? We did a little bit last time, but there's plenty of problems still. The most glaring one, besides collision, is this integer kind of forced to have numbers because like that's how we get somewhere in a vector, right? We have indices to get places. We need whole numbers to get there. So like our key type is kind of forced to be numbers right now, but our goal later is to like make a real phone book. String names. Use string names to get somewhere in this vector to store stuff. Convert strings to indices. Convert doubles to indices somehow. That's what we want. We like to use any kind of type. We like to use any type at all for our keys. That would be really nice. Because then we can make a real phone book. Okay? That is our goal, and so we need a way of like turning a string into a number, right? Because then we could use it as an index. Turning a double into a whole number. Turning a character into a number. Turning a cloud into a number. Turning a picture into a number. You can look up somebody associated with their photo. I don't know. So that's kind of where we'd like to be. Okay? Questions about that? So pie in the sky dream is I want to map T1s to T2s. Any type to any other type. Okay, that's the goal. And what's kind of keeping us from getting there is the idea of maybe potential collisions when we shrink down whole numbers, and then how to get whole numbers in the first place when we want to start with any type. Okay, so that's, I promise those words coming out of my mouth will make more sense as I give examples, but that's the answer. And then the whole squishing process, we need to think about that some more as well. Okay, so let's go back to the idea of like ints. Ints as keys. Ints are places to, like, we want to associate some large number like a phone number and with some other value, and so we need to put it as we need to somehow convert it to an index of our tiny little table that does not have tens of millions of indices. All right, we've got like large keys, small indices to place those keys. Okay, so again, reverse phone book example is a good one. Let's say I've got a vector with 6 things in it, or capable of holding 6 things. Index 0, 1, 2, 3, 4, and 5. And like I'd really like to associate, I don't know, maybe that's a 4-digit phone number, I don't know, 1284 with high, like the string high. I'd like to really associate 4876, the number, with long. And so there is no indexed 1284 in this vector, right? So somehow we need to get this number and turn it into one of these indices. Same with this one, because then we could go there and like store the high or store the long. Okay, and that's how we could get it back. So we need some sort of process to like take this and like turn it into 2 maybe, I don't know, or take this and turn it into 5 maybe. Like there's got to be some math involved, and one of the math ways of doing this is to do mod 6. Right, because if you did mod 6 on these numbers, 1284 mod 6, that would do division by 6 and give you the remainder back. The only possible remainders, but when you divide by 6, are 0 through 5. It goes in cleanly, or up to 5, because if it went in with 6 left over, just like it would go in another time, right? So that's how that works. That's one way to squish your indices down. There are other ways. All right, so that is technically a hash function. So we talked about that slightly before, but what that means is all this idea of a hash function, which you'll be reading about if you have not started already, is just a way to get a number, right, given a value of any type at all. All right, so when you have ints, you already kind of have a hash function, just like use the same int, but then you also need to shrink it down. Some people consider a hash function to also do the shrinking. Some people just consider it a way to generate a number given a value of a type. I'll think of it this way, but I might conflate the two. All right. So yeah, the number that you generate also needs to eventually be one of the indices of your table. Like you get your 1284, somehow maybe convert it to 42 if you have size 50 indices. All right, size 50 table. Hi mom. Maybe a hash function is a way to take, like, I don't know, function h takes this value to this value. You also can make other hash functions, h prime, that take strings to numbers. There's a way, right? There's ways to think about converting strings to numbers, because then we could use those as indices. That's where we're going. All right, so that's exciting. And if you have normal ints, you can use the modulus. That's a very nice, easy way to make it work. I can always take a number, shrink it down. If you got a whole number already, make it one of the valid indices on your table. That can be your hash function. All right, so for example, if you have an array or vector of size 50 where you want to put your stuff, here it is, let's say. You got indices 0 through 49 to work with, and that's conveniently what you would possibly get back if you did modulus by 50. So indices 0, 1, 2, 3, all the way to 49 are possibilities. And yeah, if you did, let's say you wanted to insert 1284, no matter what, if you did mod 50, you are getting back a value. I guess you're gonna get back like 34 or something, right? You're getting back a value between 0 and 49 for sure. No matter what the value is, mod 50 on a whole number, always going to give you something within that range. And so, yeah, every one of your indices is likely. It's a potential one that's going to be hit, and that's beautiful. All right, so that is kind of the idea. You need a function to take whatever you want to use as your key type, big numbers, strings, down to indices of your table, because you want to use those these values essentially as fancy lookups, right? Fancy indices to look something up with. You need real indices at the end of the day. You need to turn your big numbers or your big strings into indices then. That is what we are forced to have. And a hash function is a way to get a number out of anything, a whole number out of anything. Okay? Any questions about that? Does that make enough sense? Like, can you think of a way to like turn hi mom into a number? Well, strings are made up of characters, and characters have ASCII codes, which are numbers. Maybe we knew some math like that. I don't know. So that's stuff you can think about. All right, we'll get there. But yeah, let's have a slide on that. So how in the world can I make a lookup table using non-whole numbers as keys? There's plenty of things that we could think about here. Say you had doubles. You wanted to use doubles as keys, like 3.14. You could just round it, I guess. You'd have a whole number at that point. But then like 3.15 would clash with the other one. You have to deal with that somehow. That might not be the best way, but let's think about strings, right? So our goal. Let's say we want a real phone book. I'd really like to be able to insert keys that are people's names and map them to integers, their phone numbers. Maybe that's my phone number. All right. And if we're doing it in the way we're doing it, then this needs to turn into an index so that I can put this at that index. Yes? That's what needs to go on. So somehow I need to turn a string into an index of a hash table, of a lookup table. Okay? So we need to be able to convert strings to numbers. We need a hash function that takes a string and gives me a whole number back. Okay? That's the goal. So here's one way to do that, if you think about it. Do I want to do it this way? Yeah, I'll just do it on the slides. You can implement this one day, all right? So, okay. Every string is made up of individual characters, we know that. And every character is secretly a number. We've got the ASCII table for that. So everybody, some people got in a room back in the 50s or something, and they all decided on the encoding of all the Latin characters. Like apparently, look at the decimal column. Apparently, the capital letter A is the number 65 as bytes. The lowercase a is 97, and they go in order. Lowercase b is 98. Lowercase c is 99. Here's some punctuation over here. So like everybody's decided on new numbers for every character. All right. So a was 97, right? And all right, that means that if we want to turn a character into a number, we can just give its ASCII value back. That's one thing that we could do. Give back the encoding of that character. Like A, if you see A, if A is your phone book name, somebody's name is just A, you can just give back 97. There's a whole number that you can use as an index now. Maybe you need to shrink it down though. Isn't that cool? So then it gets a little more complicated when you have like AB. Like what if you have this string? You have two numbers now. A is 97 in ASCII land. B is encoded as the number 98. How can we combine them somehow to get a bigger number out of both of them? You can do some, like, you can add up 97 and 98. You can multiply 97 and 98. Those are commutative operations, though, so you might run into trouble if you have BA as well as AB. You get back the same value if you use plus or times. There's fancier things that you could do, but that's the starting point. Does that make sense? Like there's ways to turn anything you could possibly think of. You could think of a function that turns a string into a number, that turns a double into a number, that turns a character into a number, that turns a picture into a number. All right? Because it's all just binary at the end of the day. Just extract that if you want to. I don't know. You have a very large number that you have to shrink down. Does that make sense? Any questions about that? It's very philosophical for the day. Okay? So yeah, maybe a hash function on strings is take every character and do something with the ASCII values. You can combine them. You can convert them to like some sort of base 128 thing because they're 7 bits long. But yeah, there's a way. There's a way to do it. And now you can use strings as keys of your lookup table because there's a way to get like a number out of Lawton, a number out of anybody's name. That's so cool. If you would like to get the ASCII code of a character, you know that if you have a string, you can go to s at some index I to get a character out. And if you want the ASCII code of that character, you want to convert it, you want to cast it to an integer. And then one way to do that is with a static cast. You say static cast into an int, please. So highly encourage you to try to make a function, bless you, that converts a string into a number. Like takes a string, return type is int, and watch it work. Isn't that cool? So yeah, I think that's what I wanted to say about just the idea of a hash function. It's just some function that you can write in code or in math that takes some value of any kind of type, a picture, a string, and gives back a whole number, because whole numbers can eventually be turned into indices and used for looking up stuff. Okay? Any questions about that process? It's a little philosophical today. I think it's a cool idea, though. All right, so I got a question for you then. Please let us go to the buy clicker page and do attendance. I will eventually stop that as well. But here, please get into groups, discuss your weekend, say hello to each other, and then answer this question. Here's my idea, all right? Let's say that we want to make a hash table, and we have some options for keys of our hash table. We want to use these things. Keys are things that are used to look up values. Like if it's a phone book, the name was your key. You're using the name to look up their phone number. All right. And let's say we want to make a hash table that holds all the students in this class, maybe including me, if you want to. And so we need like a, I don't know, size 50 vector or something. And we want one entry for every student in the class. Maybe we'll store their name associated with each of these keys or something. Like, all right, whatever we decide on as the key, maybe we'll save their name associated with that, your name associated with that, like Lawton. Maybe something like that. Here are your options. Do you want to store the birth month of every student and teacher? Like, do you want to put, like, map September to me, for example? That can be the key that looks me up. Do you want to map the day that every student was born? Like some of you were born on the 1st, some of you were born on the 2nd, blah, blah, blah. Today's the 30th. Do you want to store the year? Do you want to map the year that every student was born or teacher was born? So yeah, I want you to think about that. Like we got a vector, and we're trying to put people in places, and we want to make a hash function that kind of like takes some values, right? I guess we could store whole numbers very easily, like September could have been a 9, so that's not too bad. But like we've got a vector of a certain size where we want to place all the students in this class. We want to map them from one of these keys to like their name. Which is the best option if we get to choose any of these? Does that make sense, that question? What is the best option to store students? Because I think you can see that there might be some issues with some of these. Yeah. So yeah, please try that. I'll leave it open, and I'll give you a few minutes to discuss. What will be the best key type, the thing that you want to use to look up some students' names? All right, I think our voices have died down. Was that enough time to think about this? Like, what's the best option? Maybe none of them are good, and the answer is D or something. Like, we'll have to think about it, but let's see. Did everybody get an answer in that wants to? Give me another 10 seconds, let's say. Because you could use any of these, but I guess the option is which is the best? Which is the best option? Let's see what we're thinking. we have all agreed, mostly, that B for sure is the best one. Could somebody who picked B tell me why? I think that would be a good answer, yeah.
It's the most unique out of all of them, more specific.
Good, yeah, uniqueness is important. I think we all know that there's more than 12 students in this class, so that kind of ruins the idea of using a birth month, right? Because if there's 2 people born in September, like, September's going to map to which of them, right? You see the problem? Same with the year. I mean, there's a decent range of student ages at least in community college, but a lot of you guys are probably 18 or 19, right? So you're born in the same year, and so like, who maps from, I don't know, 2025 minus 18 to their name, right? There's going to be a lot of overlap for sure, right? And so that kind of leaves this one. At least with days of the month, you got at least 30 of them, 31 sometimes, 28 sometimes. That's going to be the most unique, right? There's probably a couple of us that were born on the same day of the month. Like some of us were born on the 30th, for example. And so we have to fight for that one, but there's going to be the least amount of overlap. Does that make sense to all of you? So there's got to be a way to deal with this, but yeah, just think about the graphs of all these. Like probably a lot of students born in January, blah, blah, blah. A lot of people born at the end of the year usually. And then the year all the students were born, maybe there's a bit around, but like 18 or 19 years ago, there's a ton of you in those ranges. But like the day you were born is usually pretty random, and so all of you kind of look like that. And so that's probably the best way to split up your values among as many values as possible, to split up your keys into as many values as possible. Okay, so I would pick B as well, and yeah, that's kind of the issue. There's some clashing going on there, and I hope that makes sense. Any questions about the question? You see it? And so yeah, they could all be used as keys, but there's going to be clashing, and the fancy word for that is collision in a hash table. All right, so oh no, we have some collisions. How do we deal with that? All right, so like, say let's just pretend, let's make it a very easy example. Let's say we've got a hash table, we've got a lookup table / hash table with only 4 indices, 0, 1, 2, and 3, and we'd like to map keys to values, and the keys are just integers. So we want to map integers to integers. So like, here's our original keys. That is not a good looking art. Original key. And then the value I want to map it to is this. So let's say I want to map 87 to the number 42. I want to map 113 to the number 73 or something. And I need to take these keys and shrink them into valid indices of this table. And so I need a hash function that does something, shrunk key. And let's just say for reasons, that this key gets shrunk into the index 2, and so does this one. And so they're both fighting for index 2, where we want to store our 42 and our 73. Does that make sense? It's like when we go here, you can put the 42 the first time, and then you come back and you're like, oh yeah, 113, I want to use index 2 as well. Oh no, it's being used. I want to put 73 there also. Can I do this? Because that's kind of what you want, right? That's what I'd really like to have. So we need to deal with that, all right? There are a bunch of competing ways to deal with collisions because it's a fact of life. You can't get around collisions when you make a hash function. There's always going to be certain things that map to the same number or to the same index. And so you have to have a way of making them either share or split up. This is a valid option, actually. Have them share that index. Store not just one number, but like a vector inside of the vector at each index. Does that make sense? You could do that. So that's a thing. Let's talk about it. We need some terms first. Okay, so every piece of your hash table, every index really, the metaphor is it's a bucket that can hold on to stuff. So we say bucket. So here's like your little hash table, your lookup table. It's got indices, and each index is called a bucket. So this is a bucket. That's not too hard. And then we know that we have hash functions now. Hash functions are ways that take a value. It's a method to take a a value of any type, like a string or a double or a char or an image, and convert it to an integer, because we need to use that to get to a bucket. All right. Eventually, you might have to shrink it down with like a modulus. Some people consider that to be part of the hash function. Some people don't. And then, yeah, it should always be the same. Like if you try to hash your hi mom string once, it shouldn't be random. It should give back the same value every time you hash it, because you want to go to the same index, right?
Yeah.
That would be a problem if that used randomness or changed. So it's got to be a pure function, we say. Yeah, something like that. So a hash function is just like some function that takes a value like 42 and gives you a number back that potentially is a valid index of your table. All right, something like that. Yeah. But you might have collisions. 77 might also go to 7. So there's different ways to put stuff in your table. Like maybe they're all going to this index. You can put two things in an index. That's fine. That's called a collision, right? So that's what's going on. And yeah, you can make hash functions that take arbitrary types. Maybe hash function h is also able of taking hi mom, the string, and converting it to some number 1234. And then you want to shrink it down as well, like maybe with the modulus to get like, oh, it's going to index 5 or something. I don't know. Something's going to index 0. I'm placing it there. Okay? That's how it works. There might be collisions, but kind of the setup is you've got keys of a certain type. Maybe it's a string, it's a phone number, it's an image. You use a hash function to get a whole number, an integer, a non-negative number that could eventually become a valid index, right? A non-negative number that maybe is large, because maybe, hi mom, if you do some weird multiplication on ASCII values, it's going to give you a giant value back. As long as it's not negative, that's fine, because you can do a modulus, right? You can then shrink it. That's kind of the next process. Shrink it, and then you have an index into your lookup table. We index into your lookup table, into lookup table. You got a bucket to go place something, and then when you store it there, like you store the value associated with that key at that index. Store, and you put the value there. That's kind of the setup of hash tables. I will draw a little box around this in rainbow, so you see that. Whee. Does that process make sense to us? You got some arbitrary key, like a name. You want to run a hash function to get a value, a whole number back. Maybe it's too large. You shrink it down to get a valid index of your hash table, like which bucket should it go to, because that's what you're going to use to look it up as well. And then you go there and you put the value at that bucket somehow. If there's a collision, you got to deal with that. We still need to talk about it. Okay? Are there any questions about that? Does that process make sense? I've said it a few times in a few different ways, but it's just all pictures so far. Is it okay? It is a little complicated. I guess we might as well have a concrete example. Here, let's run this idea like on paper. So let's say, okay, I will give you a hash function. We'll do it all right. Okay. So let's say here is my, I don't want to use rainbow anymore. Here is my lookup table, my vector v. Let's say it's got 5 buckets, 5 indices. So indices 0, 1, 2, 3, and 4 to choose from. And let's say that I've got integer keys mapping to string values. This is what I'd really like. I'd like to map these keys to these values. And I'd like to take the number 5 and map it to the string blah. All right. I'd like to take the number 10 and map it to the string hello. Okay, so integer keys mapping to string values, so it'll just make a vector of strings, kind of. And then here is the hash function I'm going to decide on. Hash function. How am I going to get an index back? What will I do? My hash function h is going to give back x mod 5. All right, that is the exact hash function I want to use. Whee. Okay, so that's very concrete. And so let's see what happens. So I've got the key 5. I want to map it to blah. So this key is not a valid index, so I better, or any key, I need to run my hash function on it, all right, to get a real index of my table where I want to put the thing, and use that also to look it up, right? So I'll also get that same index back when I run it if somebody wants to look up with the key. So that's going to go to 0, right? And so I'll place then blah at index 0. Yes? That's what's going to happen. And then when I go and I want to say insert 10, the value 10, map that to hello. Again, I'll run my hash function, get an index back. Now I got 0 again. All right. And so I'll go to index 0 and I'll see that something's there. Whee! And I don't want to give up, but I notice that there's no room, right? No room here. If it's just a vector of strings, I'm kind of out of luck. No room for hello. But I wanted to put it there, right? That's where it was supposed to go. Oh no. There's always going to be collisions sometimes. So we need to deal with that because we want to put we want to put 10 mapping to hello somewhere in this table. Okay? So that's kind of what's happening. That's what we know so far. Does the concreteness help? Does that make sense? So that's what's going on. That's kind of what we know how to do right now. We got a key, hash function, get an index, go to that index, put the thing there if we can. If there's a collision, we still need to talk about how to resolve that. Okay? But like that's the name of the game for a hash table. You got a key, you can go look it up later now. Like if you come back and you say, hey, 5, what is associated with you? You run the hash function, get an index 0, you go to index 0 and say, oh yeah, blah is associated with 5. That's constant time. That's quite nice. All right? So that's beautiful. And I think that's getting us places. All right? So let's deal with the collisions now. Are you ready for that? Because there's a couple different competing schools of thought to deal with these collisions. And they call them open and closed hashing. Okay? So here's the secret. If we have two options, we can either reuse this index or not reuse this index. And that gives us two ideas. So if we would like to store the values that collide outside the table somewhere, in a different place maybe, that's called open hashing. And then if we want to store the values that collide somewhere else in the table, like the table's all we get, it's closed off to any other options, it's called closed hashing. All right. I like open hashing. I think it makes the most sense. And so I'm going to force you to implement that one. All right. So I'll show that to you. So open hashing is this idea. We'll do exactly this example. We want 5 mapping to blah and 10 mapping to hello, and they're both going to index 0. You can have them share. If you want to open up the table, that's okay. So what we can do, one option, and this is the option I'll have you implement. You got all these indices, 0, 1, 2, 3, 4, but you've got 2 things at index 0. And what you do is, instead of storing just the string that maps to that takes the key and like it maps to that value, instead of just storing the value, what you will store is a list of pairs. All the keys and value pairs that could go to this index. Okay? That's the answer. So at the start of time, in open hashing land, you will have an empty list at every index. Empty, 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 empty. Okay? That's what's going on. That's how that works. And you can put multiple things in every list. So every index has a list that can grow and shrink. All right, that's what's happening. And so the second you say, oh yeah, 5's mapping to blah, but that's at index 0, then you're going to go to index 0 and store that key value pair. Remember that, okay, at index 0, somebody may come looking one day for key 5. I am keeping track of key 5 and it's mapping to blah. Does that make sense? You can place that fact there. And that helps, and that's perfect, because when you come along later and say 10, oh, 10 needs to map to hello, what index am I going to store that fact at? Index 0. You just go right back and like, all right, I've got a list there. That's fine. I don't have to update it. I don't have to replace anything. I'll just like push back another pair to remember that, oh yeah, somebody may come looking one day to this index for the key 10, and I just need to remember to give them back hello associated with that 10. All right? Does that make sense, that process? Think you could implement that? Mm-hmm. Just at each index, you store a list of all the key value pairs that have been placed there by the hash function. Like you got to that index somehow. Somebody's going to come looking later for either 5 or 10. When they get here, you need to be able to distinguish between the two, right? So you can't just store blah and hello at that index because now you're not sure which key mapped to which one, right? You must also store the key now. Does that make sense? There's no other option. Otherwise, you forgot what goes where if you have... if that happens. Okay, so that's open hashing, just like it's a vector of lists of pairs, key value pairs. All right, so list. So when you see open hashing, like think list, like outside of the table we're storing more stuff, kind of. So every index is like a pointer to a list somewhere. Closed hashing is like, all right, I can only use indices. So here's an example of closed hashing, which I will not have you implement. If you take CSCI 26 with me, I'll force you to implement it there. So if you have only 5 indices again, and you stored, well, the first one you inserted was the key value pair 5 mapping to blah. That hash function took you to index 0. You saw that index 0 was available, and so you're allowed to put your 5 mapping to blah there. Like 5 mapping to blah. Again, you need to store the key and the value. It's going to be a vector of pairs still, key value pairs. You can't just store blah for reasons that have to deal with collisions. So, all right, that's where you put that one. And then you come along and you say, all right, 10 needs to map to hello. Your hash function takes you to index 0. So that's where it needs to be stored. But oh no, index 0 is in use. In closed hashing, you need to go and find another index now. So there's a way of like figuring out what's the next index to search for. If I started at 0, what's the one that I should go next to? A simple strategy, it's called a probing strategy, is to just like, all right, you started there, just go to try the next one. Try index 1. And then we see index 1 is open, and then we'll put 10 mapping to hello there. And for the same reason I hope you can see, due to collisions, I need to save keys as well as values. Because if I come looking for, hey, hash table, what does 10 map to? If you go to index 0, right, it's going to take you to index 0 first, and you only stored the blah, then again you think it was blah and it was not right, yes? So you just see that, oh no, that 5 is mapping to blah. Okay, there must have been a collision. Let me follow my strategy to get to the next place that 10 could have been inserted. And then you find this one. Okay, yeah, 10 maps to hello. You kind of see that process? Again, it's on paper, but I think you can put it up not too bad. All right. There's different ways to find. You got to go find an open index. All right. For insertion. And then you need to be able to trace your steps when you look up a value, because it's always you're using a key to find the value associated with that key. Okay? Questions about that? I just have a lot of pictures today. This is a little bit of a complicated idea. I know. But we get constant time on average. It's very nice. It's a great trade-off for this complexity. Mental complexity, not time complexity. All right? So yeah, let's do a picture of open hashing with all these ideas now. We can understand it, okay? So let's say I want to make my phone book. I got keys, I got values. I want to map actual strings, all right? So like key Lawton maps to value my phone number. All right, I want to store my mom's phone number as well in my phone's phone book. Mom maps to some other number. Okay. And let's say I've got a very tiny hash table. I'm going to use open hashing. So every index is really a list. Boop, boop, boop. They're all starting out empty. Lists of pairs. Okay. That's what's going to go there. And so, okay, I want to map Lawton to this value and mom to this value. So these are the keys. They need to become indices. I'm going to use those to get somewhere in this vector. Okay. So I need a hash function. Let's say I got my hash function, and those give me indices, right? I'm running my hash function on Lawton, and it gives me 0. All right, index 0 somehow is what, like I used the ASCII values and I shrunk them down. I got index 0 for this particular table. All right, and so what that means then is I'm going to store the pair Lawton 8675309 at index 0. I'm going to add that. I'm going to push it back to that existing list. Okay. Whatever's there, don't delete it, just add on to it, because multiple things can be stored at that index. This is a very tiny table, so you're kind of forced to have a lot of collisions here. So, all right, you're going to store the pair. Lawton is the key, and the value was this phone number. Okay, and now that's what the list looks like. So if you come back later and you ask for, hey, what does Lawton map to, because I want to know, then you'd again run the hash function to get to 0. You'd go to index 0, you'd scan through the list looking for the key Lawton, and you give back the value. Does that make sense? It'd just be a loop at that point. You have to go through potentially many things. Any questions about that before we insert the next value? All right. So I hope you're seeing it. We'll do some coding at the very end today. But all right, let's say that mom, according to our hash function, we do some weird stuff with the ASCII values, get a number, shrink it down, and let's say the index is also 0 for fun. So that means then, okay, we're going to go to index 0 and place the key value pair mom 5555555. Okay, we're going to place it there. We're going to push it back to the list. Let's say You could push front if you want. There's competing options here. But the list is going to change now. It's going to have two pairs in it. It's going to have that one and this one because they both hash to the same index, mon and this number. And so this is fine. And that's also why we needed to store the keys as well as the values, because if we come later and we ask for what does mom map to, the hash function will take us to index 0. We'll see this list. We'll scan through the list. We'll iterate through it. We'll go look at all the keys. Lawton, does that match mom? No. Mom, yes, cool. Here's the value associated with that. Does that make sense? That process of going through that list, because that's where the hash function took us, get to the value by matching it with the key. Okay? That's pretty much the process. I think that's most of what I wanted to say, and I believe that you could implement this. I think, yeah, that's open hashing in a nutshell. Every index has a list. You're going to store key value pairs there. You'll go looking up by the key. The hash function takes you somewhere all over again. Okay? That's why it's important for the hash function to never change. Don't let Lawton map to 0 and then also sometimes 1, because then you're going to get confused, right? It's going to always give you back the same value. Always the same. For a particular sized vector, of course. So, okay. Yeah, before I do some actual implementation stuff, I do want to kind of tell you a little bit about table sizes. This is important. It will become important one day if you ever implement your own hash tables in industry or something. You can read about this more in your book, but you should be using a prime number as your table size for mathematical reasons. That will help make sure that all of your data, your hash function, hopefully is also giving you back with equal probability any value, but that will help make sure that your data gets spread out evenly, all right? So let's say, and let me show you why. So let's say you had a size 24 table. That's not a prime number, right? Very, very divisible by things. So what would happen then for your size 24 table when your hash function, let's say it was very easy for the kinds of things you're inserting to get back a multiple of 12, some multiple of 12 from your hash function, and you're using a size 24 table. If you're going to shrink down, right, you're getting these potential values back from your hash function, then you got to shrink them down, right? What are they going to get mapped to when you do mod 24? 12 and 0 and 12 and a lot of 12s and 0s, right? See that? That's a problem. That's a lot of collisions. We don't like that. So there's plenty of other numbers that are like 12. Maybe your hash function gives back multiples of 5 for some reason based on the values that you like to insert. It doesn't matter, all right? But there's a bunch of numbers that could be like that. A prime number would solve all of those problems. No matter, even if your hash function was weird and it gave back multiples of something usually, it would solve the problem if you use a prime number size table, okay? Because here you do mod 24. If you had a size 23 table, you do mod 23, right? Mod 23, getting back values between 0 and 22. Again, let's say you had all these values. These were your values that you were hashing, or the hash function gave you back these values. If you did mod 23 on them, you get back these values. It would wrap around as much as it could just due to the nature of prime numbers. Give you 12, then 1, then 13, then blah, blah, blah. All right? It would wrap around and give you all the different options. The only time you'd have issues is if your hash function gave back multiples of 23, which was the size of the table itself. You can't really solve that problem. You're kind of forced to deal with that one. But that's the best you could hope for, right? No other patterns would cause you trouble. Does that make sense to us? At least at an intuitive level. That's quite nice, right? So yeah, I think that's what I want to say. So yeah, the plenty of numbers like 12 when you have a size 24 table is just think about all the numbers with factors that are in common with 24. Things that can be wrapped around very easily would have a similar problem with the size 24 table. All numbers with factors in common with 24. And so you know that if you want to limit that issue, just have a number with the minimum amount of factors, a prime number. Okay? So yeah, I hope you see that and that makes sense to you. I think I'm ready to give you some more concrete ideas with code now. Is that okay? Ready for that? I'm eventually going to code up open hashing for you just at a basic level. You can copy and paste a bit of it in a future lab. So you're welcome. So let's do that. So let's do open hashing. We're going to use lists at every index. There are multiple options here. It doesn't have to be lists, but we're going to choose lists because that's what your book talks about. It's a very common one to first learn. And so that means we're doing exactly this. At every index, we're going to store a list of key value pairs. That's open hashing. All right. We're going to open up the table at each index. We're going to look outside of it. We have some other room that we can place things. So at each index, we store multiple key value pairs. That's not very legible. Something like that. Okay. Multiple key value pairs. Very important to store the key as well as the value. Another name for open hashing is separate chaining. Like you're chaining along these key value pairs. They've got synonyms, but I'll say open hashing usually. Yeah, every index of the table stores a list of pairs because we can't just store the value itself, right? Because if we got rid of these keys, we wouldn't know like which one was associated with lot and which one was associated with mom when you have a collision. You have no clue anymore. Got to get those keys there too, so you can look up. Okay, so yeah, let's do that. And I've drawn this picture for you already. I'll make it small so you can look at it, but I kind of want you to try before I go to code. All right. So here's your picture drawing time for the day. You can break out Paint if you want. I don't need you to enter in your answer anymore, but let's say you've got a table of size 5. I honestly don't know where to put this for you right now. I'll put it up here for a second. You've got a table of size 5. Whee. So let's say this is my vector B. I want you to try to draw the rest after I do the first one for you. Table of size 5. So 0, 1, 2, 3, 4. At every index, you've got an empty list, right? Because you can store multiple key value pairs eventually. So right now I've got a bunch of these going on there. Boop. Empty, empty. That's what it looks like at the start. And let's say we want to store integer keys and map them to string values. Okay, so it's very easy to shrink down integer keys to a valid index. So we'll deal with that. Let's say I want to map these values to these values. So 5 maps to high, 1 maps to mom, blah, blah, blah. Let me insert the first one for you. And we'll go from there. So if we want to insert integers into a size 5 table, what's a good way to shrink down those integers? What will I do? Modulus 5. Very good. Does that make sense to everybody? That's a way to, for sure, always get back a value between 0 and 4. So I'll take, for this first example, I'm trying to map 5 to high. Which index does it go to? Because 5 is not a valid index. I will do mod 5. That will be my hash function. And think of that as the function itself. Okay, and so that will take this 5 to index 0, yeah? And so that means I want to go to the list at index 0 and add the key value pair 5 maps to high, because somebody may come looking later for that value. Okay, that's what I want. 5 maps to high. And honestly, I think that's a good enough. I don't think I need to show this to you anymore. We kind of just did it. So yeah, please try to do the rest in that style. Are there any questions about the question? Break out Paint, break out a piece of paper, collaborate with your neighbors, see if you can all agree, like, what is this table going to look like by the time you've inserted everything? Okay? So please give that a try. I'll give you a few minutes to make a beautiful picture for yourselves, and we'll go from there. There's going to be collisions. This is a strategy that deals with that. Open hashing is a strategy that deals with collisions. Nice. Let me know if you have any questions. Another couple minutes. Try it out. All right. We'll do another minute and then we'll come back together, okay? All right, that's my timer at least. Were there any questions that came up as we were trying it? Did it make enough sense what you needed to do? Can you kind of see how it's going to translate to code? Vaguely, at least. So yeah, let me try to do the rest, and we will go from there. Let's do the hash function real quick, just to like shrink everybody real quick. 1 mod 5 is still 1. 6 mod 5 is also 1. 25 mod 5 is 0, and 12 mod 5 is 2, yeah? So those are the indices those things will be placed in. And so it looks like index 1 is where 1 mapping to mom is going to go. That's the next thing. And so it's going here. We're going to like push back to that list, the pair 1 and mom. Okay? So that's the next thing. 1 map into mom. We'll place right there. And that's the list so far. Does that make sense? we're going to have a collision, of course. We're going to go back to that index right now. And then, okay, 6 maps to hello. Oh, no, that's also going to index 1. I better also push back to this list because I'm going to this index, finding this list. It's got stuff in it, that's fine. I'm just always doing pushback. You could do push front if you want. It does not matter as long as it's in there somewhere so you can find it. Because the goal is like insert and lookup. Those are your two options. Those are your two operations that you care most about. So, all right, 6 maps to hello. Gonna go right here. Just like that. So that's that list. And then we come along like 25 maps to blah. Oh no, that's going to index 0 where we've already got something, but that's fine. I can push back to that list, the pair 25 mapping to blah. Always got to save the key as well as the value so you know which of those values was associated with which key. Because somebody's going to come looking to this, at this index, see this list, and be like, oh, was it high or was it blah? And now you'll be able to distinguish. That's beautiful. Okay, that's all that so far. Still good? All right, one last one. 12 maps to A, so that's going to index 2. We're going to put that key value pair 12 and A there. It's always the original key. It's not the shrunk key because it's all like, you know, you're at that index. That's where the hash function took you. It's the actual key itself. It goes there. So this list becomes 12A. Boop. Just like that. And that, I believe, is going to be the end of the story. And so indices 3 and 4 are unused. Oh no, maybe we could have had a better hash function. I don't know. Something like that. So yeah, that's what the table will look like. And you can come along later and look up stuff. Be like, all right, what did 6 map to? Use the hash function again. Gets you to index 1. Go through this list. Find 6. Give back the value there. You can also change it if you want to. But like, that's the process. Does everybody see that process? Any questions about insertion or the potential lookup later? It's fun. All right. So yeah, let's just spell out everything that I've been saying on some slides, and then we'll actually code it. Okay. So here's our algorithm for looking up something. Let's say we've got, I don't know, we've got key K that we want to look up the value for. So something called K, some variable value. We would like to go into the table at the right index, right? Maybe K was 6. We want to shrink it down and get the hash function's value back, go to that index, and go searching through the table for that key. Okay? So go to the table at the proper index and search through that list for K. Where is the proper index? It is hash of, I guess I'm calling it K. It's hash of K, and you may need, like, this may be a giant value. You can do mod the size of your table if you still need to. Okay? So that's kind of how that's going to work. So we had a hash function. Maybe we were looking up something, and we got a value back. Okay? So let's say that we've already got this one. Let's say we've got the 5 high, 25 blah. Oh no. Something like that. So there is our, let's say that's the index we go to. It's like, all right, I want to look up my key K is 25 or something. I'm going to run my hash function on 25. I got back 0. And then I want to iterate through the list. Like, okay, I go to index 0. I see this list. What do I do there? What do I find? What do I look through? So I want to iterate through it then. I want to find key 25 somewhere there. That's where it would have been placed, where it inserted there. Search through each pair until you find the corresponding key. You'll look at the first one. 5, is that 25? No. 25, is that 25? Yes. And then if you find it, then you'll give back the value associated with that key, because that's the whole point of a hash table. We have some keys, we're mapping them to values. Okay? That's how that works. Potentially you looked up something that was not yet inserted. It was never inserted. It was never going to be inserted. Like 30 or something would also go to index 0 with our old hash function, right? 30 is nowhere here. You'd have some way of saying that it wasn't there as well. You could throw an exception, something like that. Okay? So if you didn't find it, you got to return something back that's like not found, like -1, I don't know, empty string, null, throw an exception, something. You got to give back a way of telling the user, like, hey, that thing wasn't there. Okay? So that's important. And that's going to be lookup. Like you got 25 was your k value. I don't know. Let's say that k was equal to 25. In this example, you hash it, get to an index, there's the list, go through that list until you find that key, give back the value associated with it, because that's the whole point of a hash table, associating values with keys. Does that make sense on paper? You see it? So yeah, I've just said it in a bunch of different ways. I hope that's making some sense. All right, and I will code it. I still promise to code it for you. All right. And then, yeah, insertion, that's slightly harder, I would say. Again, we can do the same thing. Let's say we've got all this still. Boop. Here's my hash table at a certain index, and I would really like to insert a key value pair 30 mapping to foo. That's what I'd really like. And so the very first step is, all right, what index is this key going to take me to? All right. So for key k, you call the hash function on k. Maybe if you need to do the modulus outside, you do that still. I'm going to hash my value 30. And I will get back 0 again, right? And so it's again going to take me to this list. That's why I copied it here. And so I'm going to place it there, right? At that index, you need to add a new list node if the thing that you're inserting was not already there. So this is new information. We haven't said this yet. Because what if somebody comes along, they're like, hey, I'd like to insert 25 mapping to bar. Do you see a potential problem if you were to do what we were talking about already, where you like add a new list node with 25 mapping to bar, right? Now you got two 25s in this list. You see that? That's a problem. So if it's already there, what you want to do is you want to update it. Does that make sense? That's very important. So update it to bar. If it's already in there, just change the value at that pair. You see it? Only if it's not already there, okay? So if it's already there, you update it. So let's just go back to our original example where it was 30. And okay, it's not there. If it's not there, we're good. We can add a new node, but you want to search through every node. It's a search process even when you're inserting because of this, all right? You want to search through every node, find and make sure that none of those keys are the ones you're about to insert. None of those are 30. Check, they're good. And so for this example, we're just always going to push back the key value pair. Okay, we notice that there's no 30 yet, so I'll push it back here, and I'll put 30 mapping to bar in this list, just like that, okay? 30 mapping to bar, just like that, and it can go there and be happy, okay? So it has to be the key value pair. The key is necessary because, like, if you only store the values, you're like, which one was with which key? So you need those keys. And yeah, just remember that you do need to search when you're inserting. That's a new knowledge from this slide only because we haven't, like, I didn't want to complicate things too much until now. But you want to update if it's already in there. If somebody comes along, they're like, I want to map 25 to bar now, please. You got to search through your list again. Be like, oh, 25 is already in there. I need to change then. I don't want to add a new node, 25 mapping to bar as well, because now you're confused. You got too many things. That would be space. That would be wasting space complexity, I guess. Just change the value. Okay. So if it's already in there, update it in the existing pair. So there's always just one thing of that key in this list somewhere. Okay. And that is insertion. So insertion is kind of doubling as an update, potentially, if that key is already there. Okay. I think that's what I wanted to say for insertion. Do all these bullets and these pictures make enough sense? So I'm finally ready to give you actual C++ code. Are you ready for that too? Okay, so here we go, finally. So here's what the types will look like. I'm going to make a pair type. It'll be a struct. Let's do phone book stuff. So string, key, integer value, there's my pair. I'm going to make a list of pairs, like a vector of lists of pairs, yes? That's exactly what's going to look like. I need a hash function that takes a string to an integer, yes? I need that. I need a way of inserting and looking up into my hash table. So insertion is going to take the hash table itself, which is a vector, and at each index I have a list of pairs, yes? A vector of lists of pairs. I need that. And then a key and value that I want to put in there, okay? I want to do that. And then finally a lookup is you give me a hash table. I'll just do a function-based hash table stuff. You'll eventually be doing class-based hash table stuff. So you can steal most of this, though. Got your hash table, vector list of pairs. You got the key you want to look up. and then you want to give back the value, which we've hard-coded to be integers. Okay, give back the value associated with that key if it's there. Maybe throw an exception, return -1 if it's not there. Okay, so do those types make sense before I implement it? You see why they need to be that? All right, we are finally ready to go to code. So this is open hashing. Boop. I don't want to give too much away, so I'm gonna make it the world's worst hash function for you. But here is the setup. I will steal all these. Let's see if it is at all easy for me to paste from PowerPoint today. Not bad. Nice. Okay, so I want vectors and strings. Vector and lists. Vector and list. And string. Oops. List. String. So I want all those things. And so there's my struct pair. Let's make it look pretty. Do like that and like that. And then I've got a string hash function. I've got these lookup things. And then kind of here's how I want to use it. I want to be like, all right, I better make a hash table in main somewhere. Vector of list of pairs, hash table. And then let's make it be of size 5. There's a resize function to do that if you want to do it later. So now hash table is a size 5. Hash table variable is a size 5 vector, is of size 5, and all the lists in it, because it's going to resize, it's going to have at every index a list of pairs, and it will default construct them. The default constructor on a list in C++ is emptiness. So, and all the lists are empty as they should be. All right, so that's the start of time. And then let's say I want to insert some stuff. So insert into hash table. My hash table is called legitimately hash table. Let's insert my name mapping to this number. There we go. So that's what I want to be able to do. So maybe I'll give my cat a phone number. I will give my mom a phone number. And then let's also have this work for updating, right? Maybe I get a new number, like, I don't know, the next smaller one or something. Insert should also be updating, all right? So if we now look up, see out the result of looking up in my hash table, which is called hash table, the value 1, I should get back the number that ends in 08, right? Because it needs to have been updated properly. Let's do a couple. Lonzo, mom, and then let's also search for something that's not there. All right. I didn't put dad's number in there. Oh no. What's going to happen? We have to decide. What do we give back? So yeah, let's do. All right. Here's a very simple thing so that I don't give away too much of your lab. I want you to write a real hash function on strings. Like your book will talk about kind of how you might want to do it. I gave you some ideas. You can just like add ASCII values, multiply ASCII values if you really want to. But there's fancier ways. So you can look it up on the internet. But here is a horrible hash function. Every string maps to 0. All right. So don't do that in your lab, please. Give a real hash function, make a real one, but that's good enough. Gives back a number. It'll work. They'll just all collide, every ultimate amounts of collision. So okay. So now let's do insertion. So our job for insertion is all this. Okay. So the very first step is we need to figure out which index of our hash table are we putting this key. All right, because it's always a key value pair we're trying to insert. Let's hash the key and figure out where to go. All right. So hash the key to get the index, and then potentially the string hash function will give back a large number. We always want to shrink it down. So let's assume that a hash function just gives back some number, and we need to shrink it down later for our table's purposes. So and then shrink it down, because like this hash function on strings, it doesn't even know about the table. It doesn't know the size of the table, so we couldn't even hope for it to give back a number that we could use yet. So let's shrink it down in our insert function. Okay. Alternatively, you could pass the size of the hash table to the hash string function and have it do it there. But let's say this. This is our index where we want to search. So hash string on the key I'm trying to insert, because it's a key and a value that I'm trying to insert, map one to the other. So there's the number that I got back from my string hash function. It may be too large, so I'll mod it by v.size. All right, now it's a valid index for sure. Okay, So that's what I want. That's the first step. Okay. And then I want to go to that index and make sure this thing that I'm adding is not already there, because only then can I push back a key value pair. If it is already there, I want to update what's there. Okay. That's important. So yeah, then I want to go to that index, IDX I've called it, and see if the key is already there. All right. If so, just update it. All right, that's what we want. Just update it. So here, I'm going to use references to make this easy on myself. So let's say v at IDX. That's the list I want to mess with, right? Let's give it a name. Let's call it, it's a list of pairs, right? I'll call it L, and it needs to be a reference, because otherwise I've just made a copy of something and made it outside the vector. I want to actually use the list that's inside the vector, so I want to make it a reference to a list of pairs. Does that make sense? So if I didn't have that reference, I have just copied what was in the vector to L. It's a local variable. If I mess with it, I'm not changing anything in the vector itself. Does that make sense? The vector is also being passed by a reference. So just give me the list as a reference so I can call the thing L that I want to go through, and it's actually part of the vector still. Okay, that's important. It's memory stuff. Okay, so I've given a name now just to make it easy on us. The list, this is the list I want to modify. I want to go through / potentially modify if it's a new value for that key. So, all right, I want to go through now every pair in this list. And again, I want to go through it as references. So for every pair reference, call it P in L. Because again, if I didn't put this ampersand here, I would have made a copy of that pair that was inside of that list, and now it's not affecting the original vectors list. Okay, so like keep it all inside the vector right now. I've called each pair that I'm looking at P. Go and see if the key was there at the pair P that I'm looking at right now. For example, like I'm looking at the 5 high pair. I'm looking at the 25 blah pair. Because it could have been, like 25 could have been the thing I'm trying to insert. Right? Or if it's 30, we'll get through them all. All right? So, all right, see if the key was there. So remember what pairs have. I've called it key and val inside of that. So p dot key and p dot val. So if p dot key is equal to the key I'm trying to insert right now, that's the one I better modify then. So if p dot key is like it's 25, here I am at the pair with 25 as the key, I just better update the value. That's all that needs to happen here. Okay. So all right, just modify the value there. Modify the corresponding value by saying, all right, p dot key is the key. It's got a new value to have. It's val. Whatever it was before, we don't care. p.val, whatever it was, we're going to get rid of it and replace it with val, and now we're done. All right, we're done. There's no need to do anything else. There should only ever be one. Like that's the invariant we're going to keep here. I can just say return from this void function. Like there's nothing. You don't have to go look through any other pairs, right? You've done your job. You've done the insertion. You're finished. So the second you find the thing, you just update it and you're done. Otherwise, if you get through the whole list, every pair in it, you didn't see anything, you didn't return, you're still here, that means this was a brand new key. It was a brand new key when insert, maybe it was 30, all right? So you just push back a new pair that is the key and the value together, okay? That's what you want. So otherwise, we're still in here, we didn't return yet, so we didn't update. Otherwise, add a new list element to this list called L that I've said at this particular index. It's all there. So if we got here, that means the key was not yet in the list. Okay, so that's what's happening. So add a new pair, we'll push it back. So pair, we'll call it new pair, equals the pair is the key and the value together. That's a way to make a struct really quick because it's like key then value, it's key then value. Perfect. So I can say that. So there's my new pair, and I want to add it to the list called L. Well, I'll push it back, let's say. So I'll say L dot push back this new pair that I've called new pair. All right. And now let's put it in the table. All right. So that if I zoom out, that is our insert function. And I think it's going to work. I don't think I forgot anything. Are there any questions about how this code turned out? You see every little piece of it? Get the index where we're going to go look through the list of that index, potentially update something. If we didn't, it's a brand new thing. Add the key and the value because we need that key to look up later. Okay. All right. If we are happy, let's do lookup now. So we've got a table. We've got lists of pairs at every index. What do I want to do? I've got a key that I want to go and find. Again, I want to run my hash function to figure out what is the index of this table then associated with this key, because that's the list that I want to go look through, right? So I can copy a lot of this. Boop, boop, boop. So this one, there's the index I want to go to for that key. Again, it's the same one, right? Because that's where it would have been inserted. It's important to keep it the same like that. Then I want to go to that index and see if, I guess, we do still want to see if the key is already there. If so, there's no updating anymore. It's just return the value. If so, return the value. Whee. And this is the list L I want to. I'm just going through it now. All right, there it is. If the key is anywhere in this list, I can give back the value it was associated with. That's the job of this function. But we might get through the list having never found something. Maybe like we were looking for 35, something that was not there, okay? Then we'll have to figure out, like, what are we going to do? Do we want to throw an exception? Do we want to return -1 because we're giving back an int? Something like that, okay? So, okay, I will iterate now through my list. And again, I can play kind of the same game here. Like, boop. We again want to see that if the key was there. We're hoping that it was there if we're trying to look it up, right? So go through every pair in the list. We can take it by reference for fun. Should be taking it by constant reference if you really wanted to. So see if it was there. If it was equal to there, we want to give, not modify anymore, but give back the corresponding value. It's p.val, whatever was associated with that key, return it. Does that make sense? So go, I got this key, maybe it was, I don't know, 25, get the index where it might live, which in our example was 0, go through that list, go and find the pair that had 25 as the key, give back the value blah that was associated with it. All right, that's how that worked. So yeah, does that part, that's the main part of the lookup. Does that make sense? The only other thing we have to consider is, what if we didn't find it? What if we got through the whole list? We still have not returned anything, so that's unfortunate. Whatever. What shall we do? So if we got here, that means we got through the whole list. We didn't find the key, right? That means the key was not in the hash table. Oh no. We have options. We can return some value that's the type we care about, like an int, because that's what we're forced to return here. Return some value / throw an exception. You have options to indicate that we didn't find the key. Bless you. Find the key. Okay, so just to make it easy on myself, so I don't have to include any other libraries, I'll just say, if it's an int I got to return, I'll say return -1. Because if these are phone numbers, -1 is a phone number everybody agrees does not exist. So cool, I can just return that, and whoever tried to look up can just compare against that to see if the thing was there or not. Okay, so that is lookup, and here is all the code on a single page. Are there any questions about this one? So like you got a key you're looking up, somebody's name, I guess, in this case. Go to the index associated with that name. There's a list of pairs there. Go look through all of them, find that name, and give back the phone number associated with it. But this is a phone book. But if it wasn't there, -1, let's say. It's an invalid phone number. Okay? So yeah, let's watch it work. Unless I did something wrong, which is very possible. But I tried to copy what I did last time. Open hashing. Look at it go. So it inserted. And did it update? Yes, it did. Cool. It's not 09 anymore. It's now 08 for me. And all the other ones are fine. And then something that was not there, we noticed and we gave back our little special value to indicate that. Cool. So yeah, eventually I'm going to ask you to implement this yourself as a class that is doing hash table-y lookup stuff. But this is a function version of it all, and you can steal a lot of what I did today, so you are welcome. I think that's all that I wanted to say. Are there any questions about this? Of course, you'll be getting this code. You can look through it. do whatever you want. Your book also has some great animations and things, but if we are happy, that I think is where I want to stop for the day. Any questions about anything else we talked about so far on hash tables? All right, and yeah, let me just confirm. Please do attendance if you have not. I will stop that in like a minute. Yeah, I do want to give you some other things, but that could be a Thursday problem, so I'll stop the recording now.